Hello, this is Dr. Henry. So, we're going to take some more notes on chemical bonding. We've covered a little of this before, but it's good to go over it again. So, the first thing we're going to do is we're going to look at the three different types of chemical bonds. And the first type is an ionic bond. And the big thing to remember is this is a chemical bond that results from the electrical attraction between large numbers of cations, right? That's not a very good cat, and anions. And I don't have a drawing for anions. Just remember those are negative. So the positive cations are attracted to the negative anions, and it makes a very strong bond. And in a ionic bond, the electrons are transferred. That's the key thing to remember. Ionic bonds form from a transfer of electrons. You have electrons going from a metal to a nonmetal. The nonmetal becomes negative. The metal becomes positive. The other main type of chemical bond is what's called a covalent bond. And this results from the sharing of electron pairs between two atoms. And there are two types of covalent bonds. And you can think about this if you have to share something. Like let's say you have to split a pizza with your sister or your brother. Just because you're sharing it, does that mean everybody gets it equally? Or maybe you have to share a car or something else like that. Sharing doesn't always mean equal. So there's two types of sharing. There's what's called a nonpolar covalent bond, and this is a covalent bond in which the shared electrons are shared equally by the atoms in the bond. And then there's what's called a polar covalent bond. So these are the key words here. We have a polar and nonpolar covalent bond. In a polar covalent bond, the bonding atoms have an unequal attraction for the shared electrons, and there's a unbalanced distribution of charge. It'd be like if you shared a pizza and one person ate 5 pieces and the other person only got 3 pieces. That would be a polar covalent bond, unequal sharing. And then the last type of bonding, and we haven't talked about this before, is metallic bonding, and this occurs in metals. And it's the chemical bonding that results from the attraction between metal atoms and what's called the surrounding sea of electrons. And this is kind of a key thing. Like if you're going to remember anything for metallic bonding, most people remember what's called the sea of electrons. And basically in metals, there's a lot of vacant d and p orbitals in their outer energy levels, and those are overlapping. And so what happens is the electrons can move freely throughout the metal. And the valence electrons don't really belong to any one atom. And because of that, we get what we think of as the characteristic metallic properties. So metals are good conductors of heat and electricity, especially for electricity. Electricity is really just the movement of electrons. So if these electrons are free to move around, that's why metals are such good conductors of electricity. Also, when we were studying the periodic table, we learned that metals are shiny, or a fancy word for that is luster. And what happens is the orbitals and the energy levels in metals are very close, so it's easy for the electrons to get easily excited. So just sunlight or light shining on the metals causes the electrons to absorb energy. They jump to an excited state, and they emit light upon turning to a lower energy level. And that's when the shininess comes out, or when you see the luster. Also, metals are malleable. They're ductile. They can be drawn into a wire. They can be hammered into thin sheets. These are all words we've had before. So basically, since metallic bonding is the same in all directions, metals tend not to be brittle. They can bend. So normally when you try to bend something, if the electrons are stuck in place, it's going to break. So in a covalent or in an ionic compound, you try to bend it, it's most likely going to break. In a metal, the electrons can move. So when you're bending it and the nuclei move, the electrons can move with it, so it doesn't bend. Like if you take a piece of copper wire, you can twist it, you can bend it. Eventually, if you bend it too much, it'll break, but it's much more malleable and ductile than covalent or ionic compounds. Now, let's look at ionic compounds versus covalent compounds. And we did a claim evidence response writing on this. We had the lab on this. So this should just be review. So remember, an ionic compound is composed of positive and negative ions, and they are combined so that the number of positive and negative charges are equal. So it should add up to 0. Most of these are crystalline solids. So a crystal is just a regular repeating arrangement of ions in 3 dimensions. So for the formation of ionic compounds, so a metal will transfer its electrons to a nonmetal, and metals generally have low electronegativities. And remember, they have like 1, 2, and 3 valence electrons. They want to lose those electrons. And when they lose those electrons, they will form positive ions. Nonmetals, to the right of the zigzag line, they have high electronegativities, and they want to gain electrons. Most nonmetals have 5, 6 valence electrons, so they want to gain to get up to 8 to fulfill the octet rule. And so they're going to form negative ions. And then the positive and negative ions are attracted to each other, and this forms a bond. Oh, that's the same thing. All right, sorry. So a covalent compound, then, it's a molecule. It is a neutral group of atoms that are held together by covalent bonds. And a molecular formula shows you the type and the number of atoms combined in a single molecule of a molecular compound. And you can see I've kind of in a single molecule of, this should be kind of marked out. So that's in a single molecule of a molecular compound. Now, there are 7 elements that are molecules containing only 2 atoms, and it spells out Brinkelhoff: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. And I have this on the next spot. So we can see Brinkelhoff: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Those elements actually come in pairs. They are covalent molecules. So let's compare ionic to molecular covalent compounds. The forces that hold ions together in an ionic compound is much stronger than in a covalent compound. Those positive and negative ions have a strong force of attraction between them. In molecules, the force of attraction between them are much weaker, and it's this difference in the attraction that gives rise to the different properties. So for instance, because in an ionic compound, the positive and negative ions are held together so tightly, they have very high melting points and boiling points. In covalent compounds, because the molecules aren't held together as strongly, it takes less energy to cause them to melt and also to boil. For electrical conductivity, ionic compounds, because they're made up of ions, you can get this flow of electricity, but only when they are dissolved in water or molten. Covalent compounds do not conduct electricity. Solubility in water. Does it dissolve in water? Ionic compounds are generally soluble, and then covalent compounds are poorly soluble. Crystal structure. For the most part, ionic compounds form crystals. For covalent compounds, maybe. Like in our lab, we had sugar. Sugar's a covalent compound. Sugar forms crystals. So just because it's crystal doesn't mean it's ionic, but it's a sign that perhaps it is ionic. And so those are the big differences between ionic and covalent compounds, and those come from the difference between the strength of the forces that hold ions together versus the strength of the forces that hold molecules together.